and some of them are by default more applicable in the case here of seismic, and I'll explain that as we go through it. So essentially then, what we're trying to do, if you look at this from the pixels, the first hidden layer classifies the edges. So we have this first hidden layer, and the first hidden layer will identify edges. Edges are very important, obviously, because we need to be able to move across this. We're not actually throwing this in, and I will show this on some subsequent slides. We're not throwing this in as one whole bunch of pixels. We are going to actually try to reshape this and rescale this and feed this through the neural network. But the first hidden layer classifies the edges. So we're looking at edges here, obviously, and as we progress with overlap.
Keith, sorry to
sure.
Sorry to disturb.
Hello.
But we are not able to see the pointer. Hello, I was saying that we are not able to.
Okay, let me see if I can get a different pointer. What do you suggest? I don't usually use pointer. Maybe this one? Is this easier?
Yes, we see it now.
Okay, so this yellow pointer is a bit better. Okay, so as I was saying, from this internal picture, that, as you can appreciate, is it's got millions of pixels. What we're trying to do in the first hidden layer, which is in this convolutional layer 1, we're trying to classify the edges only. And then as we move from left to right, we try in the second hidden layer, look for the corners and the contours. And so what we're doing is downsampling. And as you can see, we're trying to reduce the input dimensional space from left to right until we get down to the second layer. And then we get multiple layers here, obviously, but from the corners and the contours, the third hidden layer may isolate certain objects, and those certain objects are going to be prescribed by the geophysicist. So what the geophysicist has done, he's done an interpretation of this particular inline. He's identified potential stratigraphic traps or structural traps, and perhaps what we call direct hydrocarbon indicators, areas that perhaps represent bright spots. So if you look at this particular image here, this image could be somewhere within this major image, and you can see the subtle changes because each one of these lines that go down is a seismic wavelet. But what we traditionally do is interpret the seismic wavelet looking for seismic attributes like phase and amplitude, etc. But can we identify this bright spot just by looking at the pixels and the pictures? So this is what we're trying to do and teach this convolutional neural network to identify this bright spot or this polarity reversal based off of the pixels. And so from the corners and contours, a third hidden layer then isolates these parts of the objects. And then finally, from the parts of the objects, the fourth hidden layer categorizes these. So what we're trying to do is classify these. So it's gone through, it looked to see some of the pixel changes as we move across from left to right in each of these different areas. And because the geophysicist has said, okay, if you see these pixel pictures and this relationship within the pixels, it could be representative of a dim spot. So that's the classification side. The classification is done by a professional geophysicist in this instant. And so then what we're trying to do is these contrasts that we see in the pixels, this is very prohibitive when we're looking at scaling properties of either polynomial regression or some kind of Gaussian process. So when we're looking at it from a wavelet perspective and interpreting wavelets, it can become very laborious. But if we can help complement that process by using pictures and looking at the pixels, it could actually act as a supplementary interpretation technique. So these DHIs, essentially characteristics, are usually associated with some kind of anomalous seismic response in a trapping configuration. So it could be a structural trap or a stratigraphic trap or a combination of both. So for example, in just this one instant, if the rock overlaying the reservoir has a velocity that is appreciably lower than that of the reservoir itself, for example, a carbonate reservoir capped by shells, so the effect of the hydrocarbon is to decrease the contrast in acoustic impedance and reduce the reflection coefficient, producing this dim spot. So this interpreted dim spot may have been found and actually may have been drilled, because this could be a reprocessing. So what the geophysicists are looking for, they have potentially thousands of inlines and cross lines that together make a 3D dimensional cube of the seismic data. So in the case of the analogy I used yesterday of radiology, instead of looking at hundreds and hundreds of images of people's CAT scans or MRIs looking for disease, in this case, geophysicists may be looking at thousands of these and decide, okay, where do I need to focus my attention? Where is the most obvious place? Some of this is already done, perhaps because it's a brown field and they've reprocessed and they got another 3-dimensional data set. But in a green field, we're looking at this and we're thinking, okay, if I can train a convolutional neural network with these pixelated 2D lines, then essentially I could just let it go, throw in all the data, and it will direct me as to, hey, you may want to look at these latitudes and longitudes because these inlines and cross lines show very similar patterns with the dim spot that we've trained this convolutional neural network. Because as it feeds through all these different lines, hundreds of lines, it will put it into a classification, into a bucket, saying, I think this is the bright spot, I think this is the dim spot. So this is the technique that is used by geophysicists to try to identify and very quickly drill down and not so much automate the process, but the process will enable geophysicists to spend more time focused on the areas where there are potential dim spots or polarity reversals or bright spots, and not have to spend too much time trying to interpret all the data. So ideally, you would need about 100 images of perhaps 6 or 7 different types of direct hydrocarbon indicators to train and classify this CNN. So training it, this is the architecture of training it, and the classification that comes out in the final part of the architecture with this fully connected classification technique will then decide, okay, I see this many dim spots, etc., etc. So this is a technique that can very quickly accelerate the process of trying to identify important areas that were perhaps in a brownfield, potentially for re-engineering, where do I drop the next producer, etc. Or in the case of a greenfield, we have a seismic. We have maybe a few well logs done in exploratory wells, but the seismic is key here. And we can also do this from a seismic 3D cube. We could do time slices. So any picture essentially can be thrown into this kind of convolutional neural network to identify and classify the objects that we're looking for to help the geophysicists. Now, quite often, now in my day, most seismic sections came in black and white, but today we get all this color stuff from the likes of Schlumberger and Halliburton. So ideally, you want to convert your pixels of interest into grayscale because it makes it much easier for the computer and the computer resources to bang through some of these identifications, and the neural deep neural network will work much faster if it's based off of a grayscale. As I say yesterday, we do have essentially, let me change the color of this so it's easier. So we do have essentially red, green, blue, which is a color palette, but quite often in grayscale, especially if you're not using GPUs on your computer, you may find it somewhat slower to process all the data. So we try to convert that into a grayscale. Now, this slide is interesting because what we're trying to do, as you can see here, I've taken the grayscale of the seismic inline and I've broken it down. So this is what I mean by breaking it down into a more acceptable format as we go through and put this into the convolutional neural network. So we have the edges here, for example. So it's trying to determine edges of some of the seismic events and some of the direct hydrocarbon indicators. So a grayscale image of a resolution of, say, 2560 by 1920 consists of nearly 5 million pixels. So it's a bit of a prohibitive number of features for most predictive algorithms to use directly as an input. So a common practice in image processing consists of dividing the image, this image here, into square sub-images, also called patches or tiles. And usually you can specify this in your convolutional neural network. And quite often, once we've done that, there are hyperparameters and parameters that allow you to have the overlap and define those particular parameters that dictate how many patches you output. And the number of patches depends obviously on how high of a resolution your input data is, because high resolution data is absolutely key to becoming more proficient at using these techniques to identify some of the important structural stratigraphic traps that you'll see as you output from the convolutional neural net. Now, for example, decomposing an image, like I said on the previous slide, what we're trying to do is say for example, you let P be a patch of size B by B, for example. And if B equals 20, then P contains 400 pixels. So this is a pixelated decision on how you want to rescale or resample the input image. And so this is far more suitable for analysis as opposed to the whole image. And in general, B is an important tuning parameter, and you should choose B large enough to capture recognizable patterns in the image. And patches are often allowed to overlap in order to avoid some kind of artifacts. These are visual discontinuities that can occur along the boundaries of patches after they're processed. So B is an important area, and B in this case is 20. So as I said, you select 20 by 20, you have 400 pixels. So this P contains 400 pixels. For natural images, patches can be efficiently represented as linear combinations of elements. So these elements are known as dictionary atoms. So I won't go into too much detail there, but the reason I mentioned the dictionary is because this dictionary of atoms of B, so this would be a kind of a dictionary, you can vectorize that patch by rearranging all the pixels into a row vector of size B2. And so this is important because as we go into the convolutional neural network, we want to be able to ensure that the dictionary is going to be useful after the convolutional neural network has completed and classified the important areas that we're looking to identify in new data. So this is the training process of a deep neural network. In this case, this is an autoencoder. And so this slide focuses specifically on stacked autoencoders. And so what I mean by that, they perform unsupervised feature extraction. And remember yesterday I mentioned features are very important. And in the case of features here in the image processing, one of them may be a bright spot feature, one may be a dim spot feature. So we're trying to classify so that as we use this dictionary at the end of the training of this model, we can then apply it to new data and put the new image in there, and it should identify, based off of that training, these new features in different data sets. So briefly, the network is trained by setting the target neurons equal to the input neurons. So these are the target neurons up here, and these are the input neurons here. So there's multiple layers and a bottleneck in the middle. So this would be what we would call the bottleneck, where it's extracting features. So again, it's a process of dimensionality reduction. And so the network is forced to learn a reduced dimensional internal representation of the inputs before reconstructing them in the output layer. So as we go down through the hidden layers, it's reducing the number of neurons, but it's forcing to learn a reduced dimensional internal representation. So it's almost tantamount to the principal component analysis of reducing the input space, but still retaining variability in the data. So we're not losing any resolution. All we're trying to do is try to reduce the amount of hidden neurons, because that would also accelerate the process of training this neural network. So the weights in the output layer up here have the same dimensionality as the patterns themselves, and they constitute what we call the dictionary. So the neural procedure was used to train a 7-layer autoencoder with 50 hidden units in the case with Devon Energy when we took their I think we took about 300 or 400 inlines and about 300 or 400 cross lines, and that would represent the 3-dimensional exploration or seismic acquisition process. And then 25 hidden units in the second layer, so this would be the second layer. And then as we progress into this area, we're going from 10 hidden units, and eventually we will then move back out, because this is going to be essentially what this model is trying to do, is replicate the input, but understanding the weights it had to apply and some of the internal parameters, so that we could train the model on this data set, on these number of images. And then when we apply this to new images, it should be able to identify the different classes of images that we're looking for, such as the direct hydrocarbon indicators. And so this slide essentially focuses on the stacked autoencoders, where, for example, in this area, we may decide that this, because you can look at the patches that come out. So this part of the actual network may identify a particular feature. And so it's important to try to see the characteristics and the weighting on those and some of the hidden parameters, because we can then build a generalized model, perhaps, because this is less generalized since we're trying to identify multiple different types of direct hydrocarbon indicators. But this particular area may be just looking at a bright spot. And so we can then compose a dictionary saying we're only interested in these bright spots. And so then you can build retrain this one just off of the output from this particular part of the neurons. And so this is the dictionary thing. So this would be input data that has never been placed into the model. And all we're trying to do is use our model and then say, okay, here's another set of data. Can you identify this particular, in the case of this, I think it was a bright spot, or can we identify that within this new data set? And very quickly it would do this. And then it's up to the interpretation, because as I said before, it's not a black box where we would just want to press a button, now comes the answer. It's important for the geophysicist then to have condensed his decision cycle time by saying, okay, I put on like 400 or 500 images, now I can just focus on these images that have identified bright spots, for example. Now in the pipe surveillance methods, quite often, we did this with a couple of oil and gas pipeline companies up in Canada and also in South America now, where we're looking at trying to run drones. And so there's different ways of getting high resolution imagery to identify damage in a pipeline, perhaps the vegetation affecting a pipeline. There's multispectral imagery to identify pipeline right away, can be used in agricultural space to detect plant health, etc. There's LiDAR to create 3D digital models. And it's important then for some of these techniques, especially in the drone area where we can take surface photographs to look for potential problems in the pipeline, corrosion problems, etc. And thermal identification allows for possible defects also externally. And these provide a ton of data, a ton of pictures. And what I showed you previously with the seismic data is essentially what you can do, run through the same kind of autoencoders, convolutional neural nets, all the different architectures, but the images obviously are different and not seismic subsurface images of, they are images that we can get from the drones. And so the important thing is you have a good set of data images, but then you need to decide which of the convolutional neural nets is most appropriate for identifying the images that are going to be addressing the business problem you're interested in. The last slide I have here on the computer vision, for example, again, is from a pipeline where you're trying to detect the positions of anomalies in such a pipeline, where we have this thing called a pig that essentially runs through the pipeline, traveling inside, detecting data, and potential leaks and corrosion and metal loss and dents. We can actually see some of these images and try to run it through an autoencoder. Most important thing is that as I keep stressing, with a deep learner, which is a convolutional neural net, we need a lot of images because what we're trying to do is classify different objective functions, if you want. What are the issues we're trying to identify? And in the case of pipeline, we may be trying to identify different leading indicators to leaks or corrosion or metal loss, etc., dents. And if you have these images, then we have to be able to classify that, and so that when we run new data, new image data, we can then see which of those classifications it falls into. So that's more convolutional neural net. This is gaining a lot more traction these days in the oil and gas industry, certainly in the midstream and in refineries as well. The use of drones is providing a lot of data, and also in the seismic area. The subsurface area of the seismic is probably a little more contentious because geophysicists tend to be more particular about their first principles. Now we're going to go into a drilling optimization using ML techniques. I'm going to look at one of multiple different issues. This issue comes up a lot with certainly NOCs, is the rate of penetration. Quite often when it comes to other oil companies like some of the majors or independents, it's more around operational expenditure, and so we're looking at cost per foot or NPT, non-production time. But we did this recently with rate of penetration because they were more interested on how fast they could drill their wells. So one of the main goals of drilling optimization is to reduce the total time, essentially maintaining the risks. Obviously, HSE is still foremost in everyone's mind, but maintaining the risk as low as possible. And one way to achieve it is through a selection of optimum drilling parameters prior to a run. You know, selecting the suitable drill bit, drilling fluid type. Another approach relies on real-time analysis in order to optimize the operational parameters, such as bit weight and rotary speed while drilling. Drilling wells is obviously very challenging in the oil and gas environment, especially offshore, and suggests large capital expenditure on a wellbore's construction. So in order to optimize the drilling process, real-time decision-making must be established. But we can't get to real-time drilling until we've looked at some historical data and identified some events in space and time. Some of the issues we get in drilling, like stuck pipe, for example, we need to be able to understand that it's a multivariate problem. Drilling can be very complex, but what is your low-hanging fruit? What is it you're trying to solve primarily in drilling? Is it rate of penetration? Is it cost per foot? Is it trying to reduce the energy, the hydraulic, mechanical, specific energy used in drilling? Or is it NPT? And NPT can be a very controversial measurement, and I won't get into it here, but non-production time. And so it's important to identify that business problem before we can do an inverse process and identify the data that's going to be most appropriate to solve that business problem. An ROP is one of those. So rate of penetration, how fast can we drill? What kind of drill bits do we need, etc. And that is all dependent, obviously, on the types of rocks we're going through. And so real-time decision-making can only be done once we've done some analysis through the machine learning to understand the historical data, because within that historical data, we have some events in space and time where there have been stuck pipe, for example, or we may have drilled several wells within a reservoir, some of them very close together, but the rate of penetration has quite a range of different different results, and obviously we want to try to maximize our ROP. And so cluster analysis I mentioned before, if we've drilled half a dozen wells and some of them are really bad when it comes to the ROP accuracy, we need to understand why. So despite many efforts, theoretical, experimental efforts throughout the years, modeling the ROP as a mathematical function of some key variables is not a trivial process. This is due primarily, I believe, to very highly nonlinearity behavior of the multivariate interactions of all the different operational parameters. And we mentioned this yesterday in an introduction to drilling when we're looking at torque, weight on bit, and other variables. So how does a machine learning methodology really help us in trying to optimize ROP? There's a fragile balance really between the cost of drilling a well and the intrinsic value gathered from that well, because obviously when you drill a well, you've got to maximize the placement of that well, so through a drilling program, and that usually comes beforehand with the exploration and production data, seismic data, to maximize the placement of the well. But some of the key cost drivers such as ROP and NPT, the non-production time, and the days to total depth. These are important KPIs for many oil and gas companies, because especially in today's economic market where it's becoming more expensive and the profit margins are decreasing because of the price of oil. And so ROP, the rate of drilling a well per foot, is one of the most important that I've seen more recently when it comes to drilling new wells, primarily in brown fields, to re-engineer that brown field and try to get more of the hydrocarbons that have been left behind. The value that you can get out of addressing some of these costs, these KPIs are important to justify and quantify really the value of each well. So maximum reservoir contact is key, obviously. So if you have a directional well, you want to make sure that you're drilling within the reservoir and have maximum reservoir contact. Is critical for efficient hydrocarbons capture. And maximizing the ultimate recovery obviously is dependent on the wellbore quality. So well integrity is also a very important aspect of drilling and completion when it comes to a well. And the literature, there's a lot of literature out there from Society of Petroleum Engineers and other sources that dig into some of the machine learning techniques we can use in getting the best out of a particular well. So this slide essentially illustrates a possible methodology to maximize ROP. It's a little busy, I confess, and I apologize for that, but the ROP is related obviously to the speed with which drilling is performed, and maximizing it is one of the critical factors affecting the commercial success, obviously, of the drilling operation. So the rate of penetration prediction with mathematical models, as I mentioned, is somewhat helpful, but can we complement that with a machine learning methodology as well? So again, I go back to the hybrid approach. Not a lot of people like using that terminology, but what we're trying to do is not move away from first principles. We still want to understand the relationships between some of the variables that are important when it comes to drilling a well, but we understand the functional relationships, and how can we put inside the context of that a data-driven machine learning or deep learning model based off of all these different data sets and values within those data sets. So ROP depends on many drilling variables and has complex relationships like the operational parameters, formation, properties, comprehensive strength, well hydraulics, the borehole shape, mud properties. There's a very complex and multivariate relationship. And so that's why sometimes the first principles and some of the algorithms really don't provide the necessary methodology or process to really fully appreciate or understand what maximizes ROP. And so combining the traditional models and machine learning models into one predictive model can be achieved using some aggregation functions, the core basically of ensemble models that I mentioned yesterday. And random forest is one of those such random ensemble techniques. So as we go through a process, so I mentioned several times yesterday that a process is very important because a process can be repeatable and scalable. So once you built your model for a particular area, we would like to generalize that model so that if we moved into a different part of the field, we can still use that methodology or process. And so it has to be scalable and repeatable. And so in this case, if you look at the orange box here, there's actually some new technologies currently I saw most recently in the literature that apply micron-sized rock fragments and drill cut-ins. So not just sensor data, where we're looking at sensor data, perhaps collecting some of these variables. We can also look at the cut-ins, and these drill cut-ins can provide us with a parallel understanding or interpretation of the reservoir, for example. So this includes high resolution CT scans, for example, to resolve rock texture or geomechanical and isotope analysis. So mineralogical analysis or geomechanical analysis of drill cut-ins, especially in the unconventionals, and microbial DNA analysis technologies, all these are all pretty bleeding edge technologies but they provide data. So I think you're getting a sense of the fact that there's loads of data out there, but how do we make sense of this data? And this is where data mining, machine learning, deep learning can help us and complement some of the first principles that we've been talking about and which all of you are familiar with. So once we've gathered the data, we go through that, remember the SEMA process or whatever process you find is most appropriate for yourself or for your corporation. Because we want to do data quality control, impute missing data, outliers, and normalize data. And recall that if you're getting data in real time from sensors, for example, there could be some sensor problems, the sensor may be down. So we need to make sure that the sensor is providing good data, and we need to interpolate or extrapolate some of the missing time series data. So again, this process is very important to follow before we actually design a machine learning or deep learning algorithm to do predictive modeling or prescriptive modeling. So the difference between predictive and prescriptive, as you know, we're trying to predict an event that may happen in space and time based off of previous events that we've actually seen within the signatures of the data that we've identified as being most important to predict the ROP, and what is the most cost-effective ROP, and which is the best way to drill a well based off of maintaining a high rate of penetration. And the prescriptive model, then, if you ran multiple models and you have an upper and lower boundary, you can actually come up with the prescription. So if your company or yourself saw this kind of problem again in similar geology or in a different part of the world, you may implement this same workflow and come up with prescriptions. So you can build a library, and I've seen this done by some IOCs, and certainly in the case of Schlumberger and Halliburton, who are looking at trying to come up with prescriptive models within their software package, instead of just trying to interpret and understand what do I do. There is already a prescription as to how do you address these issues, because you've seen this before elsewhere. So in the case of rate of penetration, ROP models are classified essentially into these four main categories. The first principles culture attempt to understand the physical nature of well drilling, where you're describing drilling activities with analytical equations. Normally those equations are deducted through some mathematical model, and similar questions can be asked and actually addressed by statistical regression techniques, which is a very basic linear regression in this case. But what we're trying to do is move into machine learning models such as artificial neural nets, because this approach starts with the data. And data is key, obviously, and this has probably been emphasized several times over the past 2 days, but data is actually key because it's got hidden information, and that raw data has to be turned into actionable knowledge we can use to make decisions. And it serves as a basis for obtaining the predictive models. So we kind of a functional relationship. And these ML models or algorithms are able to learn how to map drilling operational parameters into another space, the ROP in this case, the rate of penetration. So we're trying to bring the most important variables that impact ROP. Now, from a first principles, a drilling engineer would tell you, yes, I already understand this, but like I mentioned before, we've had discussions where just defined basically and totally on first principles, there are questions being answered based off the fact that the data that's been accumulated is somehow pointed in different directions. And so it can be complementary, but also supplementary, because it captures the complexity of all these different activities, such as trying to drill and maintain ROP. The main similarity between the traditional models, which is out of scope of this tutorial really, and statistical models is the necessity of pre-selecting a model for ROP as a function of drilling variables. So the main difference is that a statistical model does not normally attempt to represent the physics of drill bit mechanism and the interaction between the rock formation and the bit, as the traditional models do. But a hybrid model can actually complement both the first principles and the data-driven approach. And I think that's important. And a lot of oil companies now are trying to just give a second opinion from the data and enable drillers to drill holes more effectively at a higher rate of penetration. So the data in real time is collected then from obviously drilling data acquisition units on the surface of the rig. So we can collect, for example, you know, as I mentioned, weight on bit, RPM, torque, standby pressure, the flow of the pumps, the depth of the cut. These data are depth index sampled, usually at about 0.5 feet interval. And so in this case study, we're looking at 3 wells essentially used in this study to span a total footage of some, I believe, 1,800 feet. So in order to ensure similar wells are used in the study, the data sets are selected such that the static parameters in these wells, namely the drill, string configuration, bottom hole assemblies, mud properties, these are static. These are not variables, but the nature of the drill bits could change based off of the rocks that are going through. So these data sets span 4 different types of formations. So you can see the formations here, FA, FB, FC, FD. Now I took this from a paper written by a colleague, an ex-colleague of mine, and so I'll give you the reference of this so you can read the actual paper, but I thought it was a really good high-level appreciation of applying machine learning in trying to optimize rate of penetration. So these different formation, as you can see here on the left-hand side in this table 1, they represent different rock types, and these formations were drilled essentially with a 12.25-inch diameter bits. And so these are some of the results that came out of those. And so the machine learning techniques can learn complex patterns due to the training or learning. Remember, when we build a model, machine learning model or deep learning model, we need to partition the data set into a training data set, which will contain mostly the data of 70–80%. And this is the learning phase of the model. So without having to specify an ROP model, we're not specifying anything that is first principles. So after the learning phase, the trained model can then make predictions given new inputs. So 2 classical ensembles were used. And in this study, and I'll give you the reference for this at the end, one of them was the random forest. And then we also used a gradient boosting technique. The gradient boosting technique, again, is an ensemble of trees that are essentially decision trees, but both these ensemble models have as base learners the tree models, as I mentioned before. But there is a difference between gradient boosting and random forest, and the main difference between them is the learning procedure of the trees as base learners. So while the learning phase is performed in a parallel approach based on this bagging technique, I think it's a procedure that random forest kind of falls back on, because the sequential learning adopted by the gradient boosting technique ensures that each base learner focuses on the deficits of its previous learner. So this one is learning much more efficiently than the random forest. And so Ensembler is becoming far more popular these days, because instead of relying on your decisions from a singular machine learning technique, and some of them are obviously good at what they do, but again, the selection of what type of machine learning or deep learning technique you're going to use is totally dependent on the data, and that data is totally dependent on the business problem that you're trying to solve. So you have to keep that in mind as you select the different types of models available to you, because it can be overpowering having so many different types of models. Now, when we took the data from the previous slide, we were looking at some of the exploratory data analysis techniques, and I have one here that essentially is the box whiskers chart. Now, this is good for looking at outliers within the data. So here we're looking at the bit models here along the x-axis, and some of the measures up on the y-axis. So we're looking at tool face gravity, hook load, top drive, RPM, revolutions per minute. So the abnormal data can influence the model very negatively and may restrict the model in its generalization. So if you have any suspect data that's flagged in the range validation procedure which checks if the measurement actually can be within the limits of rig limitations and acceptable trends. You can see some of that stuff in your visualization. Remember, Tukey diagrams are excellent at visualizing your data instead of just looking at a bunch of spreadsheets with numbers on. So for example, the here we're looking at tool face gravity, hook load, top drive, bit by bit model. So each different bit model will give you their impact of these different variables. So in the case of looking at this kind of box whiskers, you can see the different quartiles of the data and the values that fall within those different quartiles, and also identify quickly the outliers. So we may want to go back and look at the data set and do some editing in order that before we make the model, we can actually ensure that we have a more robust data set. So dealing with many features in machine learning problems can cause some difficulties essentially in both the data set and the derived models. So feature ranking is a technique which finds the importance of features and can be found to reduce the dimensions of the data set. Remember, features, by features, is just an interchangeable word for variables or parameters. So torque would be a feature, for example. You can see listed down on the bottom left these different types of parameters, or if you wish, features. So feature ranking is a technique that is important because it identifies the critical features and can be used to reduce the dimensionality of the data set, which is also key. And I mentioned principal component analysis as another technique. So using this technique also has the benefits of a shorter training time and an easier interpretation. And you can pretty much see if your model is overfitting, and that's important as well, overfit and underfit in the model, because we don't want a model that is just specific to that data set. We need a model that is more generalized. So it's essential to check the generalization ability of your model in data mining problems. And one of the common methods for models validation is to split the data set into training and test centers, as I keep mentioning, and then evaluate the performance based on the test set. However, the inability of measuring the generalization of these models is a weak point of the method. And so it's one of the techniques then to try to assess the model is this independent data set analyzing technique called 10CV. Now this would be in your notes because there is a really good paper written by Zhang and Yang in 2015 and Barami in 2016 that explains some of these techniques, because it's absolutely critical that you apply some kind of feature ranking and model assessment before you actually operationalize that model in the field. And so the data set is split into 10 parts, essentially. You can see the 10 parts here from left to right. And at the first step, one of the 10 subsets is chosen as the test data. So we'll choose this in round 1 as the test data. And then this procedure continues 10 times, essentially. As you can see, there are 10 rounds. And then the average of the root mean square error, or R square, is calculated for all 10 trials. And then this technique has a lower variance compared to other methods and can confirm that the model is generalized and not overfitted, and demonstrates the advantages of using a ranking technique like this. So we're trying to avoid that overfitting. So essentially the input vector consisted of 10 independent variables, and you can see these 10 independent variables down here on the bottom left. And then to perform feature ranking using this technique, it would find and identify the importance of each variable and how critical that variable is. And so essentially the selected variables were mostly consistent with the findings in literature. So we're looking here on the right-hand side, and according to the results, weight on bit and mud weight, essentially, were the first important variable. Mud weight was probably the fifth, and RPM and depth, obviously, we can take that as given, but the flow rate and the mud weight were the most important parameters with the weight on bit. So this is important in enabling us then to build our model, identifying the variables that have the most statistical impact on, in this case, ROP. And then, so when we build our model, we can keep that information to hand so that we do build a model that will actually give us a much better rate of penetration. So in this study, we're using a fast-forward backpropagation neural network. And as a result of that, we can see some of the different internal hyperparameters or parameters that will help us run that, because we've now identified the data set and the most important or critical variables that we want to use. Now we have to decide how to put the architecture together for this fast-forward backpropagation neural network. And so different values of these activation functions, for example, and you see these enumerated here. And what are the best parameters with a minimal error? So this is essentially equations we can find to see what the minimal error is. And so a sensitivity study then on the activation yielded that the ReLU, that's the rectified linear unit function, to have the lowest training and testing error as shown here in this slide. So after several simulations, the network utilized 60 neurons in the hidden layer to provide optimum accuracy in the training and validation set. So as you can see, the neural network gave satisfactory results within the coefficient of determination, essentially around 0.99, about 99% R value here. So this is the importance of, once you've identified your data as being critical as input data, we then need to decide on what type of machine learning technique we're going to use. And in this case, the fast-forward backpropagation neural network was used, but then and so testing the different internal parameters was also important to give us the accuracy. And in this case, we used a activation function known as the rectified linear unit. So this is a plot after applying that against new data. So the plot of the actual ROP, as you can see on the Y scale here, and the predicted, which is at different depths. So the predicted is the blue and the actual is the red. There's a pretty good simulation or overlap within this figure. So the R value between the predicted ROP and the actual ROP from the regression indicates that the predictions are not random, and infers that the neural network model predictions of this ROP are pretty much in close agreement with the actual ROP across the formation. So formation FD was not taken into consideration as its span is relatively small and the data modeling wasn't appropriate. But you can see here the R value, and in the case of the formation FC, we had an ROP that was predicted at 94% accuracy. So again, taking data, historical data, and dividing into test or validation and training data, the training data taking the bulk of the data, we can then train it so that training data hasn't been used in the sorry, the testing data hasn't been used in the training data, so that we can then justify and collaborate that the the model is not overfitting or underfitting. So in conclusion of the drilling, this case study pretty much demonstrates some of the practical uses of data modeling and machine learning, and to predict effectively the ROP along the entire well, considering the surface operational parameters like RPM, weight on bit, flow, torque, standby pressure, etc. So the neural network type of algorithms enabled us to capture those patterns of the drilling parameters that affect the ROP, and we set aside obviously a blind well to actually make sure and test the model. So research showed there are different ways to minimize drilling costs using these techniques. Now, down here, I'm mentioning particle swarm optimization algorithm. This is something that was mentioned to me by Saudi Aramco. I was talking to someone there called Salem Garbi. He's in charge of the drilling program there in Saudi, and essentially what he was saying is that research showed new ways to minimize drilling costs using particle swarm optimization algorithm. And the reason I bring this up is because we've talked about neural nets and gradient tree boosting, support vector machine, etc., etc. But I think to remain topical and up to date, there are new papers coming out that are investigating different types of algorithms, and one of these is being done in, I believe, the Texas A&M University. So a lot of this stuff comes out of universities, but the point is also it can come from other industries as well, where we've used these techniques. So the PSO can enable us to quickly determine the optimal parameters that can be incorporated in real time, because at some point you might want to operationalize this model and put it out there in real time. These are some of the references, and of course I will be sharing these references and the case study that came from some of these references, and there's a link there for one of those case studies. So I think we'll quickly take a break of 5 to 10 minutes, a water break if you wish, and we'll get back to looking at some subsurface well log generation and lithofacies classification using some machine learning techniques. I'm not sure, Ria, if you have any commentary or.
Yeah, thank you so much, Keith. So everyone can take a break, a quick break, and we will again meet in about 10 minutes. Okay. You may jot down your questions, and at the end of the session, when we have the live Q&A, you can ask those. Thank you.
Sure, I can start now, you think? Welcome back. I hope you can hear me okay. So we're going to look at some techniques in machine learning, deep learning, perhaps that could be useful in the subsurface to analyze some subsurface data. So what I want to walk through today are some techniques, just very quickly go over the well logs best suited for lithofasciist classification. So lithofascists, for those of you guys who aren't reservoir engineers, or it's essentially just looking at different types of rocks, litho just meaning rock, and fascists. We're trying to see from well logs, because if you remember, well logs are localized within the field. So we're trying to understand from those well logs, and there's a whole base of really rich well logs that give a lot of information about the petrophysics or the geology or the rock properties. And so we're trying to use well logs in a way to automate a classification of the different types of rocks between the wells, so that we can have a better understanding of putting together a geologic model and maybe re-engineering a field, for example. So we're going to look at some machine learning approaches to gather insights into what is known as lithofasciist classification. It's one of the most important reservoir parameters, providing a qualitative description, if you wish, for hydrocarbon geothermal reservoirs as well. So we're going to look at 3 different machine learning techniques to extract this kind of information from various well logs. So reservoir management for optimized production, as well as other business value. It's not just necessarily optimizing production. It's also perhaps trying to understand a much better static geologic model, and trying to identify locations perhaps on secondary or tertiary oil recovery, increasing recovery factor and stuff like that. So there's many business values that can be garnered from doing machine learning across a very similar data set. So in this example, for example, in reservoir management for optimized production, we're looking at just a sample of some of the well logs that are commonly collected. And so AI model types primarily used in reservoir management are supervised. Remember, I mentioned supervised, unsupervised, where supervised is more around interpreted or labeled data sets, so that we can have a functional relationship between the independent variables that are, in this case, all the gamma ray logs, etc., and the dependent variable, which in the case of production may be cumulative gas production or rate of gas production, etc., etc. Again, repeatable, scalable techniques and processes are absolutely key. And reservoir engineering then comprises one of the more important segments of petroleum and natural gas related exploration and production technologies. So by analyzing the field data, structural mathematical models and conducting experimental measures provide significant insights in terms of reservoir characterization. So by reservoir characterization, I mean, can we improve the static model before we introduce the fluid contents and the dynamic side of the model, so that we can then design a drilling plan, perhaps in a greenfield or even a re-engineering of a brownfield? So conventional reservoir engineering approaches have encountered many challenges in many facets, obviously, of reservoir analysis. Processing, cleaning, analyzing raw field data can be a pretty laborious and computationally intensive task. So reservoir engineers spend a lot of time, I would imagine, following a trial and error protocol to convert data such as seismic survey data, well logs, core analysis data, production history in a brownfield, for example, into a format that's more practical for engineering uses. And this is where machine learning can come in and be very, very critically important, because, as I mentioned before, the automation or semi-automation of data management is key, but they are somewhat laborious tasks. So can we aggregate spatial and temporal data to get a analytical data set, even if it's just for pure interpretation? But this hard data that's collected in the field and then interpreted to generate more soft data, if we can accumulate that data into an analytical database, we could then also come up with some really good machine learning processes that could complement or supplement some of our interpretation. And so artificial intelligence technologies have been gaining a lot of ground and more attention because of their fast response speeds and very vigorous generalization capabilities now. It's getting easier to generalize based off of a pretty high level geology. For example, we've managed in the North Sea to generalize something that is around compressional, depositional environments. We may need a different one for an extensional, but as I mentioned yesterday in North Africa, we did have to retrain some of our models, and models are the same, and it's the same process and the same automation of actually managing the data, but the important thing is that we just have to retrain the same model with different data based off of the different geologies and basin information. So advanced machine learning algorithms such as fuzzy logic or artificial neural nets, support vector machines, these are becoming more familiar now, as you've probably read a great deal on these. These provide really good regression and classification tools. And so most of the machine learning algorithms used in the reservoir engineering area belong to the category of supervised learning. And so in this case, what we're looking at here is a set of sequences of understanding which well log data to bring in based off of the fact that we're trying to automate a process to address a business problem. So again, it's important to turn that business problem into a data-driven problem in order to eke out the business benefits. And there's many ways to visualize all this data, and there are different types of models we can use as well. So in this case study, we're looking at well logs for lithofascious classification, essentially. So you can see some of the well logs that we took into account here, and some of the responses from these well logs. So these well logs come in a typical standard log ASCII format, which is pretty common in the oil and gas industry. Unfortunately, in the oil and gas industry, there's a lot of different types of standards. So we have energistics that essentially provide WITS-ML type XML formats for well log. And then we have other PPDM and other standards. Unfortunately, the oil and gas industry is trailing other industries in real standards. And so it's almost like we have to somehow come up with a standard. And I know that in Shell, there's a program being driven right now to standardize upstream data. And a lot of companies like Schlumberger are contributing towards that standard. But you may want to research that and see whether you want to advocate to that standard, because these standards have been done before, and Microsoft tried to do this as well. But the well logging is used essentially to investigate and characterize the subsurface stratigraphy in a well. So the single LAS file can only contain data for one well, essentially, but it can contain a lot of different data sets, which we call curves from that well. And these are examples of some of the curves that can be collected from a single well log. So in using well logs for lithofacies classifications, the first step is really to select the discriminant logs. What I mean by discriminant logs are obviously going through that process of statistically finding which are the most important logs that will give you insight to resolve the business problem that you're looking at. So some of these logs are more commonplace than others, and some logs that you may find very interesting. I mentioned yesterday the FMI logs, and in this case the NMR logs. These are expensive and tend not to be collected as much, but we can generate these logs and other logs that are very intuitive and useful from other logs, more base logs. And so the gamma ray, neutron, density, sonic, resistivity, and SP logs have a lithofacies discriminability. So they can discriminate different types of rock properties, and basic characteristics of well logs are essentially important based off of the fact that we need to be able, in the facies classification, try to understand not just the different types of rocks and where they suddenly change, what is the top and the bottom of that rock layer, but also fluid content as well. And some of these logs can be indicative of the fluid content. So in the case, for example, in the gamma ray, it measured the radioactivity level of the formations and is often indicative of some kind of clay content. So it's commonly used to separate shale from sandstone for conventional reservoirs. So in practice, because of the volume of measured samples, because we could have these sampling at a very high sample rate, gamma ray, for example, is calibrated to the fractional volume of the clay. So it's important to bring in these different types of logs in order to understand how we can use this in a machine learning technique so that we can predict from a seed well within a cluster, for example, all the different layers and facies changes based off of taking the logs from those independent wells that we haven't actually interpreted. So a professional interpretation can be used in a seeded log, and then that information or knowledge can then be very quickly spread across the other wells based off of the fact that we're going to use a machine learning technique to look at the mapping patterns and relationships between all the logs within a particular cluster. So this is a methodology. I quickly go through this slide because this is something that can be repeated for generating not just nuclear magnetic resonance logs, but also, for example, formation microimaging logs. It may have different ingredients or different logs or base logs that will generate these logs, but if we can do that, and that's a derived feature, so that would enrich the data set that we would put into a machine learning algorithm if we're going to use it for facies classification. So we would look at NMR logs as useful to understand the lithological or geological information, such as the variation of pore size distribution with depth, but it may not be measured in all the wells. So the project that we're looking at, and this project, as I said, can be used to generate other types of important well logs. The project tried to predict a missing well log from other available well logs using machine tools. And so for more specifically in the NMR well log, we could look at gamma ray logs, caliper logs, resistivity logs, and the interpreted porosity from one well at one field. And the constructed model then would be used to predict the NMR log at another field, which doesn't actually have an NMR log in that in a particular field or even a particular well bore. So the univariate, if we look here, the univariate and bivariate analysis of these particular logs. So by univariate, we're looking at just taking the gamma ray readings, and you can see a type curve. So you and we can see where that actually correlates with other types of logs within the same well. So the univariate is an important distribution that shows there are no obvious missing data, significant spikes. And so this is the process again of going through the data set and trying to standardize the data set so that we impute missing values, or maybe want to discount that particular gamma ray log because it's got a lot of erroneous values, etc. And so it's important then to walk through these different steps before we can actually generate a pseudo log, if you wish. So I won't walk through all of these. It's out the scope really of this high level introduction, but this will be shared with you so that you can actually emulate these techniques to generate M&R logs, for example, or in the case of FMI logs for cores. Because I mentioned to you yesterday, we were looking at, ENI provided us with some logs, but they didn't have too many FMI logs. So we would take an FMI log and a core, which they did in that particular well, and somehow map the relationships and patterns between an FMI log to a core. But then we go back one more step and generate FMI logs from other logs. So that then, instead of trying to core every well, which obviously they can't do, or actually generate FMI logs, which is like a 360-degree picture of the well bore. We don't have to do that either. As long as we have some basic well logs, we can generate in 2 steps the FMI, and then use image processing and convolutional neural nets to go from the FMI pictures or type curves and create a core log. And so then you can create pseudo cores for a lot of your wells, and that's currently being done by ENI in Italy. I mentioned that because there's a paper being written by them, so I might be able to share that paper with you. Features are, as I say, well log data from oil gas wells, and once a machine learning model is trained on this data set, the model will be used to assign facies to wells that have not been labeled. So there's an interpretation done by a geoscientist to actually do some labeling, because the labeling enables us to use the supervised techniques in the labeled data. We do not know what type of rocks or formation, and we only have the well logs. So we need some of them interpreted, and that would be a seed well as we go through. And any wells that are gone through the cluster analysis, all the wells within that cluster, as long as there's a seed well in there, we should be able to use machine learning to interpret all these different types of facies, and this is what I was talking about, the type curve for a gamma ray log, for example. And so this kind of response in the gamma ray log could be with sand with inclusions maybe of shale, etc. And then the bivalent or multivariate approach would be by consistently looking across at different types of logs. But if we could generate these logs and insights just using machine learning based off of some seed wells of all the interpreted logs, then this is a far more efficient way of actually coming up with a fascies classification across the whole field. So feature engineering, again, I know I bang on this a bit, but it's so key to everything, because feature engineering is so critical to developing a data-driven algorithm. So discriminating essentially raw data samples is often not useful or possible. So the data is first transformed into feature vectors, essentially with a feature extraction step. So the feature vectors and corresponding labels are used to train a classifier. And so what we're trying to do is classify the different types of fascies, and I'll explain a bit more on the next slide about that in the case study. So this aims to find a mapping from feature vectors to labels, so that when we put new data in there, we understand it's been essentially trained on feature vectors from seed wells, and how can we then identify the labels of other fascies from wells and well logs that we haven't interpreted. So this mapping is then used to make a label predictions on future unlabeled data sets. And the success of that classifier is measured by splitting the labeled data into testing and training sets, as I mentioned. And where the classifier is trained with the training data, and predictions are then made on the test data. So the predicted labels are compared to the true labels of the test set to measure the success of the training. So again, sometimes in the proof of concept phase, you would provide a bunch of maybe interpreted data or well logs, and then you would use maybe 80% or maybe just one seed well once you've done the cluster analysis, and say, okay, I know the results of my interpretation based off of all the interpretation I've done thus far. I want you to predict what my interpretation was by keeping aside a certain number of wells that you've interpreted, and see if your algorithm will actually predict what I've interpreted. And that's the usual way if you're dealing with a software company who claim they can do this kind of fascies classification. And even if you're using Python, and I will mention in the next slide a really good competition that was done by Brendan Hall. He was running this this is like 4 or 5 years ago now, but this is just one example. If you go into GitHub and you see this machine learning contest, for example, and some of you may already be familiar with this. I know it's a pretty common fascies classification machine learning technique, but it's a very good illustrative way of using machine learning and looking at well logs as the input data sets. And the actual code it's in Python, Jupyter Notebook, will go through the process of SEMA, if you wish, where it will sample the data, explore the data, go through modification of the data before it actually builds the models. And this data set was using the well logs from 9 different wells. And of course, these are labeled with a fascies type based on the observation of core. So we're looking at core data, looking at interpretation of the core data, and looking at interpretation of the well data. So these log data were then used to train different machine learning techniques like support vector machines. And we shall walk through 3 different types of machine learning technique, of which one is support vector machine, just to show the validity and the success of using these techniques to identify the different fascies. So these are the different well logs. You can see the type curves of these different well logs, gamma ray, and then density, natural log of density, and then you have porosity And so these are the different types of facies that they were predetermined. And so the intention then was to set aside some data to see if we can actually predict these facies. So the 9 different types of facies or classes of rocks that you see down here in the color on the right hand side, these are representative of these types of classes of rocks: marine sandstone, mudstone, wacky stone, dolomite, etc., etc. And so the intention then they provided, now when you go on to the GitHub and you access this, they will actually provide you with the data as well in an Excel spreadsheet. So then you can actually emulate the process and go through this piecemeal and see the techniques. Now, if you're not using open source, you may be able to emulate this in the software that you are currently using in your company or the software you currently use. You could even transfer this to R as well. But essentially what we're looking at were 5 different wireline log curves. And these are the 5 here. And these would then have 2 geologic constraining variables. You recall I mentioned constraining variables. To me, constraining variables are very important because it allows us to make sure that we contain the data-driven approach, the methodology or the algorithm, so that it doesn't create something that has no business value. So in the case of any machine learning, artificial intelligence approach to solving a business problem within the upstream, midstream, or downstream, you have your empirical formulas, your algorithms. Now you want to be able to derive from those functional relationships other features that you can add and enrich your data set, and also constrain the model so that it doesn't create something that has no business value at all. It is actually plausible and makes sense to a geoscientist or an engineer. So this lithology classification is based on these different 5 wireline log curves. And apart from the significance in formation evaluation and the geological analysis, the lithology interpretation also has practical value, not just in identifying the different rock types, but in reserve calculation at the exploration stage and detailed reservoir description at development stage. So there's a lot of business value can come out of something that seems intrinsically a simple process of just ingesting different types of wireline logs, and the data set is then run through 3 or 4 different types of machine learning techniques. I think this was open to over 300 or 400 people. Well, at least 300 or 400 people reported their results, and the one I'm going to look at is the one that actually was the champion model. So this is the data training data set that they provided across the 7 wells, and they set aside 2 different wells to validate. And so it's very important, as I mentioned, to have a really good substantial training data set that's robust. So you don't see any missing observations, or you don't see any missing values. That is taken care of in the quality control situation where you may want to impute missing values or by one technique or another, and ensure that you have a solid data set, especially if you're going to use neural networks. So after the data processing, which may convert well name formation to categorical variables. Remember, we went through nominal, categorical variables, a nominal variable, and discrete variables, continuous variables, etc., and ratios. These are all different types of variables that will have maybe different scales and different ways of looking at the data, but sometimes we may have to convert, for example, a numerical variable that has the maximum value. Do we really want it to represent the maximum value, or do we want to represent the average value? And do we want to turn that numerical variable into a categorical variable? Because some algorithms will only take categorical variables, especially in the unsupervised technique. So then the data is split into training set and test data sets, and then we can go on and actually throw this data into a machine learning technique. So in this case, this is around the exploratory data analysis of that data set, just using a different, I wasn't using Python here, I was just using another software product that quickly shows the individual types of features. So you have all these different features. These are the well logs, and you can see the distributions very quickly in these histograms. So do we need to do any transformation of that from perhaps a log normal to a normal distribution, depending on what the actual feature is? And so we had a lot of feature vectors in this training set, and the fasces here essentially weren't discrete and gradually blended into one another. So some of the neighboring fasces had to be taken into account. And so we didn't want to mislabel with these neighboring fasces because, as you can expect, it's not a clean cut between this is sandstone and this is where it starts, this is where it ends. There's going to be inclusions of maybe shell or other types of rock. And so there may be a fascist type that is obviously not just pure sandstone. And so those features can be defined as different types of fasces as we go through based off of the analysis. These quantiles, again, you can actually visualize these quantiles in a box whiskers charts, and then these are the descriptive analytics summary statistics. So this gives you a look and feel of the data and whether it's appropriate or at least in a fit condition to do machine learning. This is one other type of exploratory data analysis, a Tukey diagram that essentially is a scatter plots. And so scatter plots are a pretty familiar tool in geosciences to visualize how two properties, for example, vary with rock type. So if you look along the bottom, I've got color scheme of fasces type. Remember, we have 9 different fasces types. These are the labels. Now, by looking at the color scheme and through this scatter plot, and these are the different variables or type curves within the well logs, and we have those 5 well logs, you can see a distribution and even a fit. This is like a fit, the best fit of the distribution of the different gamma ray logs across the different fasces types. And so it's important then just to get a look and feel of that to make some interpretation and a subjective understanding of which values of gamma ray, for example, are outliers. Do we want to just keep the values within that range for that particular fasces type? So these kind of questions can be answered, and a lot of this stuff can be automated once you've set up a process, and you can ask the software to select certain well logs and certain ranges of values within that well log for each specific fasces type. So that can be generated usually in some kind of UI on some software, or that generates the code behind the scenes where you set the rules up, for example. So now we can extract just the feature variables we need to perform the classification. Again, we're looking at classification, identifying what makes up each of the different types of fasces and what are the values of the different well logs, for example. So the predictor variables use the 5 wireline values and the 2 geologic constraining variables. Remember, I mentioned the 2 constraining variables, relative position, for example, being one of them. We also get a vector of the fasces labels that correspond then to each of the feature vectors. Each of these are features. So then we applied a support vector machine. Now this is not a illustration or a visualization that you'd find in Python, but Python will do their own visualization, for example. And so these several machine learning techniques, which one is going to be best? Once you've got your data, which is in a ready state, the actual idea of generating different types of machine learning or deep learning algorithms are very quick to run. You could probably run a dozen on most software in a day. So you can quickly change, identify through some kind of assessment of which is the champion model, and then you can go into that model and maybe change the different flavors of that particular model to get the hyperparameters or parameters spot on to give you a model that is highly effective and giving you maybe 90% plus certainty that it's going to be accurate. But we also want to make sure that we don't overfit or underfit that particular model. So the support vector machine classification formulation is achieved using these features, obviously, that we mentioned. And this approach performs better than do most probabilistic neural networks. The support vector machine learning algorithm uses a kernel function essentially to compute the distance between the feature vectors. Now, the feature vectors are the gamma ray and the density, bulk density, et cetera, et cetera. So they're the features, and they throw the numbers into a vector and they compute distances between the feature vectors. So many of these kernel functions exist, but in this case, we're using a kind of a cubic function. Again, that's the process I mentioned before. Once you've identified, and if you think support vector machine is your algorithm of choice because you've done your assessment on which is going to give you the most accuracy, then you may want to go into some of the internal workings of that particular algorithm and change some of the parameters that you pass. This is the gradient tree boosting technique. This algorithm sequentially generates base models, and while building a new model, samples that are misclassified or incorrectly estimated in the previous base model will have a greater chance than essentially of being selected or assigned a higher weight. So that's the process. It's an ensembler technique. Remember, the decision tree is the kind of the building blocks, and then you have random forest and gradient tree boosting. And so the gradient tree boosting can provide a pretty good model with a high classification accuracy. And one of the things I want to draw your attention to is this ROC chart, just a ROC chart. I think it's the receiver operating characteristics, if you have to know what it means. But essentially, it's a chart that displays the ability of a model to avoid false positives and false negative classification. So quite often in software, if you run a model, you can generate these ROC charts to see if you are perhaps going to predict too many false positives or false negatives. And this can be very, very important, obviously, because we don't want any false positives or false negatives. We want accuracy on being correct. So a false positive classification means that an observation has been identified as an event when it is a non-event, essentially. So we call that a type 1 error. And a false negative classification means that an observation has been identified as a non-event when it is, in fact, an event. And so that'd be kind of like a type 2 error. So a good ROC chart, which you can see here, has a very steep initial slope. So you can see this really steep slope here. And what this slope hopefully will do is level off pretty quickly. So we're seeing this leveling off here around this point. And that is for each misclassification of an observation. So the observations are the rows of data that you're providing in this vector into this gradient boosting. And so that misclassification of an observation, significantly more observations are correctly classified. So for a perfect model, one with no false positives and one with no false negatives, the ROC chart would start at 0, 0, which it does here, and continue vertically to 0, 1. So you'd see this directly vertical line. So that would be the algorithm, the gradient tree boosting machine learning that gives you perfection. And obviously we're not going to see perfection. We don't see perfection in interpretation, the deterministic classical way. So what we're looking for then is not necessarily a perfect model, but we're looking for one, as in this case, the ROC chart would start at 0, 0. And in this instance, the model will correctly classify every observation before a single misclassification could occur. And it usually, and the higher this goes vertically, and then it starts tapering out, we're seeing a very good, probably 95% sensitivity. And so this is a very good model. And over here, you have the relative importance variables. So this will give you a listing of those variables that have the most statistical impact on predicting the fascies based off of a well that we never used to train this particular model. So that is not a bad looking model. In the case of random forests, and if you notice, we have perhaps some different relative importance. If I go back to the previous slide, we see non-marine, average neutron density, porosity log, and photoelectric log. But if we go to the random forest, we see now gamma ray log being percolated to the top as being the most important feature. So with the random forest, the decision tree, again, is its cornerstone. It's one of the most intuitive models for classification problems, but it can break down a complex decision-making process into simpler trees, but it has a tendency to overfit the features. And so that's why the gradient tree boosting, because of the internal workings, tends to be more accurate in a highly complex data set or set of variables that have a variation in the vectors. So we might find that you want to run a random forest, but you may find that the gradient tree boosting gives you a better result. And in this case, this is the software that is enabling us to quickly compare all those different models. And the champion model selected here was the gradient tree boosting. And you can see a lift chart over here that kind of bears that out. So if you're going to use some kind of model comparison software, it's important to ensure that the resultant algorithm is in keeping with the individual analysis that you've gone through at that time and interpretation. But most software provides that model comparison technique. In the case of fascist classification models with gradient tree boosting, for example, the generalizable multi-class classification model was essentially built to identify all the different lithology classes that were from different areas. And so this is just one kind of functional relationship that I saw in a really good paper written by someone called Shahab Mohageg. Now, if you're not familiar with him, I've known him for about 20 years, but he's been working on this kind of stuff. He's a professor out of West Virginia University, and he is probably the godfather of all this type of stuff in the upstream. He is a really good at data-driven analytics, and so he came up with this relationship. And there are several metrics to measure the performance of a multi-label classification model, because this is what we just built in gradient tree boosting is a multi-label classification to look at different types of classification of fasces. And it looks at the accuracy score, the precision, recall, and has a functional relationship score. And this accuracy score measures all the portion of the classes that are correctly predicted. So these precisions define the ratio of positive classes that are predicted by the model correctly to all the predicted positive classes. So this is a really good way to measure outside of the usual statistical means. And if you remember yesterday, I mentioned some techniques about XAI. Remember, explainable artificial intelligence? That's becoming far more critical now in trying to make sure that the models that are built from a data-driven perspective have some interpretability for a geoscientist in the case of oil and gas industry. Because it's important that we build these models and complement or supplement the first principles interpretation, but at the end of the day, we've interpreted the data in the latter way, but how do you interpret the results of a data-driven? And quite often they would do predictions and they would tell you the answers, but how do you know that apart from the statistical techniques that measure and the previous slide where I show you the relationship of trying to predict the accuracy, I think it's also important that this XAI is highly adopted and more people are looking at this. And this is just one technique using Shapley values. And the Shapley value is a solution concept essentially from game theory. So as I mentioned yesterday, Lloyd Shapley won the Nobel Prize for Economics in 2012, and he came up with this game theory. And it's essentially, it's a cooperative game. So it may be some kind of war game or whatever, but it's cooperation between the players. And the players, he's kind of using the analog of the players are the features. So it assigns a unique distribution among the players of a total surplus essentially generated by the coalition of all the players. So the Shapley value is characterized by a collection of desirable properties. So the setup essentially is as follows. So you have a coalition of players that cooperate and obtains a certain overall gain from that cooperation. And we're looking at cooperation of features. So since some players may contribute more to the coalition, as it were, than others, or may possess different bargaining powers, for example, it's important that we find the final distribution of generated surplus among the different players that should arise in any game. So what we're doing here in this particular, there are several visualizations that you can generate from Shapley. This actually came from a Jupyter notebook, so I will share that with you guys and how to use Shapley. But this was done in an unconventional oil and gas field in the United States. And so these are some of the different types of variables or features that we were looking at. And what we want to understand is what is the importance and how does that play within the overall interpretation that came out of the model that was used to identify the different features. And again, this is a very simple way of looking at the feature. The value, a high value would be the red and the low value would be the blue. So even though you've done all your pre-processing on the data using principal components, you've reduced the input dimensionality of your data set that goes into your model, out comes the model results, but then you want to do a further study using this XAI, explainable artificial intelligence, using Shapley, for example, and say, okay, of all the variables you use in this particular model, let's see how really, from a game theory perspective, they actually contributed and made an impact on the results that you're trying to interpret. So this is a pretty good way of looking at that. And here are some references, but I will share those in the deck at the end. We can take a quick break. I think we have probably another half an hour left. When I have one more case studies around production forecasting used in the United States, which won't take me more than about 20 minutes to go through. So it's up to you guys. What do you think, Ria? Should we take a quick break, 5 minutes, or should we just plow on?
I think let's go on, because then we have 1 hour only to complete the
Sure.
entire session. So
Okay.
let's continue. Thank
Sure.
you.
So on this one, I'm going to look at production optimization, forecasting, essentially using a case study we have in the United States. ASEMA, I don't want to spend too much time on this. This is just the process I mentioned. So come up with your own process that is repeatable and scalable, but essentially you've got to cover each of these points. The most important point, in my opinion, is exploratory data analysis, understanding and getting a feel of your data. The sampling, the modification, if you have really good hardware, IT, OT, you may be able to just suck in all the data, depends on your software and the restrictions on your software. So exploration of the data and the modeling of the data, being able to generate multiple models, and then once you have your champion model, identify the parameters within that model that perhaps you could change to get different flavors of the same model. So in this is a very interesting case study that is available, and I will share this as a Society of Petroleum Engineering paper that was written by Shell, and I worked with these guys in Wyoming on an anticlinal structure, and this was presented at a conference in Florence on using different types of geological data and petrophysical data and operational parameters. So that's a nice mix of data sets. So the data was taken from 10 different well bores, and each well bore had production login tool. So this PLT data was collected at 9 different stages. Because if you can imagine, we have this anticlinal structure, and it's like a layer cake. So these reservoirs were sitting on top of each other in this anticlinal structure. So the completion databases are critical, really, to benchmark the well performance, and ascertaining or applying optimum completion strategies is absolutely critical when they wanted to drill another well bore across this anticlinal structure. So they had these geological parameters: distance from the peak and the peak of the anticlinal structure, the dip, so we have slope, then we get into curvature, so we get into Laplacian and some other mathematical relationships. So again, we're not throwing out mathematics or physics, and some of these are first principle relationships that we want to integrate and enrich the data set before we built the neural network. And then the petrophysical, what we wanted to start off with, another good idea is that we don't really want to boil the ocean. So if in this case we wanted to maximize gas production, cumulative gas production from this particular set of reservoirs in this anticlinal structure, but we didn't want to bring in too many petrophysical properties at the time. So what I'm trying to say is you can piecemeal build out and enrich your processes and your business cases based off of an initial stage. So this initial stage was set with minimum amount of geological parameters, petrophysical and operational parameters. And then as we garnered results from that and learned how to maximize the cumulative gas production and where to stick the next wellbore, we could then enrich the petrophysical reservoir characteristics and make this into a more comprehensive business value proposition as we expand around the field and build and drill more wells. We could even optimize the drilling strategy, for example, based off of other data sets that and the completion strategies, how much proppant, for example, is being used here. So these are some of the operational parameters, because we wanted to optimize a hydraulic strategy, but we also wanted to maximize gas production. So this is deriving value from a complex interrelated heterogeneous multivariate kind of subsurface issue, especially with the different rock types we had in this anticlinal structure. So you can see on the left-hand side here all the different variables, and there aren't that many variables. Now, we did actually start off with about 100 variables, and then we decided using principal component analysis and factor analysis to just knock it down to these key variables, since they had the most influence at that time to the cumulative gas production. So I mentioned yesterday we just wanted to use a very simple fast forward back propagation neural network with just one hidden layer. And so we came up with 3 neurons that would be output. And so the engineers at Shell decided, okay, cumulative gas production between 100 and 150 MSCFD would be category 1 wells, et cetera, et cetera. So these category 3 wells is what we're really trying to drill. Our next well and all our subsequent wells were hopefully going to be category 3 wells and fall into this area. But what was the hydraulic strategy we needed to use? What were the operational, excuse me. What were the operational parameters and the values that would give us category 3? And we had to be cognizant or aware of some of the formation petrophysical parameters that would be influential on the category 3. And also the mathematics or the physics or the Euclidean geometry that we would have to come up with in order to make sure that we drill the wellbore across the anticlinal structure and hopefully get a category 3 well. So those are some of the decisions that were coming out. So if you look at this is an example of an exploratory data analysis process. So we're invoking again Tukey type charts and diagrams, and the geoscientists can begin to appreciate the complexities in this multivariate data set. So essentially, if you're looking at this, you can see a lot of different things going on in just one visualization. So we're looking at distance from the peak. So these numbers represent distance from the peak of the anticlinal structure. This is the gas production, cumulative gas production. So obviously we want to be up here, the highest gas production. And so highest gas production would be in these 3 areas maybe. And this is the distance from the peak. So again, we did a fit just to see where the outliers were perhaps on some of these values. And this is part of the process of trying to approach the critical variables and try to reduce the upper and lower boundary of values that are going to be useful for us as we go forward and make predictions on production. So this is just one example of a exploratory data analysis technique. Excuse me, I just had to take a drink there. So this is another one. So again, there's so much information you can actually portray on a visualization as opposed to just looking at numbers in an Excel spreadsheet, for example. So this is, if you can see down the left-hand side, we classified the different the different wellbores. We had 10 wellbores from which we garnered all the data that we were interested in. So first of all, we were looking at wellbore 6. And if you look at, this is the porosity, and this is the gas saturation values. So over here, we're looking at net H. So this is the pay zone that we're looking at. And the color coding essentially is the gas production, cumulative gas production 100. Let me just explain what 100 means. So I mentioned we had PLT data, production logging tool data, right? So An important thing to do, obviously wells are spotted at different times throughout the process of field development. So we need to normalize so that we can make direct comparisons. So what the Shell engineers and geoscientists decided that every well that had PLT data, let's look at the status of that well 100 days post PLT data started, because some wells started at different times and some wells are spotted at different times. So that was the kind of normalization process, and that's why it's called QG 100, which is cumulative gas 100 days after PLT data was selected. So along the top here, we see the different stages within the hydraulic fracture strategy. And so if you look quickly, you can see that we're interested in the red stuff, which is the highest gas production, right? So we're looking at stages 5 through potentially 9. The porosity values, just out of interest, you know, we would expect maybe higher porosity values would have more gas production, perhaps, depending on how the strategy was when it came to the amount of proppant, etc. But you could basically toggle through these different well bores and see immediately a response here as to which stages had the highest gas production. And this is important to note because some stages were producing water and maybe they were just producing only water. So if we wanted to drill another wellbore across this anticlinal structure, we could say, okay, stages, for example, 1, 2, 3, 4, if it was close to this particular wellbore that we're going to drill, we may not want to open since we don't seem to be producing category 3 hydrocarbons. So these kind of question and answers are important as we go forward to make decisions at the end of how we're going to actually locate a new wellbore and what will be the hydraulic strategy to actually complete that wellbore. So in this case, it's just another example of looking at it. So here we're looking at the different categories, 1, 2, 3. So this is a further delineation and categorization based on the levels of production. So in this case, we've provided a categorization of low, medium, and high QG 100 rates by wellbore. So these are the different categories I mentioned in the neural network output layer, 1, 2, 3. So this is represented then as being category 3 is where we want to be because this is the highest production data. We see the same relationship of inputs to outputs exist regardless of the production rate. So if you see the fit and also the distribution of the points within each of the different categories, they are very similar, if not the same. So although this renders no further really good insight into operational performance, it does in fact validate the artificial neural network model in terms of which input variables influence cumulative production by showing the same distribution across all stages and all categories. So we know then that from, my mouse is going crazy. So we know from this particular visualization that we have very similar distributions across all categories, be they good producers or bad producers. So we know the neural network and some of the hyperparameters and parameters within that and the weights, etc., are good. It's consistent. So we're not creating anything across the different categories. Now, what we want to do here is perform a very similar analysis of the geological parameters, right? So we looked at some of the other parameters. Now we're looking at Laplacian and distance from the anticlinal peak by stage and against cumulative production. So the gas production again is represented here. So we're looking for red dots. We're very interested in the red stuff. And the operational parameter, proppant size, as you see here, is actually represented by the size of the dot. So the higher the bigger the diameter of the circle, the more proppant's being used. And you can see down here some of the lower proppant usage, and up here, for example, the higher proppant uses. So what is immediately noticeable here is that cumulative production does not appear to be a function only of the proppant volume, but there is still clearly a relationship between the multiple dimensions of cumulative production to the wellbore design and completion activities. And so, the Laplacian and distance from peak, and these are the different stages. These are important operational parameters. And we're looking at the red dots again and which stages they appear in. And we're looking at values for Laplacian and which wellbores. We have 10 wellbores. And we can see where located those wellbores are that are the most productive and at what stages. So again, this is just firstly digging in a little deeper into those proppant volumes and relationships to production. Here we may see less proppant volume, but we still have maybe a good production. I mean, if you glide over this, you probably see the values come up. So, and then this is the distance from the peak. So we're getting a lot of information in these visualizations that can actually help us build out an idea or a decision based off of all these different interrelationships of parameters as to where we're going to put the next wellbore and maximize production and get a category 3 wellbore. So in this particular visualization, again, QG100, we have the highest production here in the red zone and here. But you see this, the size of these squares or quadrangles, essentially. What these are representative of the amount of proppant that's being used. So we have mapped cumulative gas production by wellbore, and you can see the different wellbores there, 1 through 10. And obviously wellbore 1, wellbore 9, and wellbore 10 are our best producers. And yet wellbore 10 has used much less proppant. This has used a lot of proppant because of the size of the square or rectangle or quadrangle. And so here we're looking at highest production, but the smallest amount of proppant. Now, from an operational expenditure, if we could produce this, we're going to be much better off. So does that mean less proppant volume has no impact on proppant production rates? Of course, this doesn't always have that direct relationship. So we need to drill down one level further and study the individual stages at wellbore 10. So if I show you the next one, this is wellbore 10, essentially. So in wellbore 10, we have 9 stages, and essentially then what we're looking at in stage 1 is primarily hardly any production. It could be a lot of water coming out of stage 1, whereas we have here all the good stuff, or the red high production. So in other words, what we're saying is if we can go and simulate or drill another wellbore 10, which is a category 3 wellbore, we will close in stage 1 next time. We understand from the mathematics through the Laplacian, etc., differential equations that we've applied to some of these mathematics of the Euclidean or non-Euclidean mathematics that we apply across the anticlinal strata. We can locate that wellbore, but we can also understand which stages to shut in. We don't need stage 1 if we have a wellbore 10 type of new well that's going to be drilled across this anticlinal structure, because we don't want to generate water. And again, the proppant volume. So maybe, certain stages, they seem to be pretty much similar areas. But if we had one in here that maybe had a huge stage and a huge amount of proppant, we may reduce the amount of propanol. And we can do this for frac fluid and other types of operational parameters as well. So in other words, at the end of the day, you get these different variables coming in, going in through a neural net, and you get a well score, and then we can see on the data that was set aside that we haven't used in the training, what category 3 characteristics we need in order to score another category 3 well within that anticlinal structure. So essentially then in production forecasting, what we're trying to do, I showed this yesterday. This is a slide we saw, but it bears repeating because the time series modeling algorithms assume that the series is stationary. And I mentioned yesterday we were going to go into a bit more depth on what stationarity means and how important it is, because the time series is said to be stationary when the mean is not varying locally, i.e. it's a constant with time. So additionally, the variance and covariance of the ith term, if you wish, should not be a function of time. It should the mean, the variance, and the standard deviation should not vary locally in order to get stationary requirement. And that's important when you're running recurrent neural nets or ARIMA or the UCM time series techniques. Again, and this came out of several customers that we started primarily with Saudi Aramco several years ago, but we've repeated this before, is that clustering is important because, like I keep mentioning, if you can cluster wells with similar characteristics based off of, in this case, these are some of the variables we use to do the cluster analysis, and it's an unsupervised technique, we can then identify all the well group A that have low porosity, high permeability, low production, high pressure, et cetera, and so you can define them as good wells, bad wells, and then you can put those on your base map across your geologic model and see where these wells are actually located, because they may not, all the good wells may not be in one part of your field or one part of your reservoir. So this is a good way to see how effective, for example, artificial lift techniques or secondary or tertiary water drive techniques were working. And this is what happened in Saudi Aramco. And then it also enables us then to run in parallel some of the techniques of data-driven forecasting workflows, so that we can run them in parallel, one in group A, one in group B, one in group C, because we're working with data that have very similar values. This is just really a visualization to show how you can look at oil and gas by date, and it's not an interpretation, it's not a forecast, it's just really just trying to get a look and feel and looking to see if the reservoir production data is non-stationary. So the stationary aspect is important, as I said, to trying to attain. And the declining trend, you see a declining trend here in both the oil and gas, and this declining trend makes the local mean production rate as a function of time, essentially. So hence this time series is non-stationary and needs to be stationary. So stationary time series, as I mentioned before, has properties there where the mean variance and autocorrelation, these are all constant over time. So we need to be able to just look at this and say, well, we know this is not a stationary time series. There's some kind of, sorry, not a stationary time series, this is a non-stationary time series with influences that we have to decompose from the time series before we can actually do any kind of ARIMA models, etc. And this is looking at some time series data. And these are some of the things we might want to decompose. For example, we have trends and outliers. You know, we might want to get rid of some of these outliers. And the trends could be cyclical. So For example, at what time do you use historical data to help you forecast the future? Because if you have a well that's been overly stimulated or a lot of well tests, there's going to be some cyclical characteristics of that data, and we may only need to use the previous 6 months, because if you go back 2 years, that doesn't really help us in what's influencing the immediate future, and therefore the forecast, if we used all this data, would not be as accurate as if we used something after a post-stimulation. And then the ramp up is something else that we may want to look into in order to decompose or and take out. So different patterns are observed at different field levels, regional levels or operator levels. And so we need to be able to get our time series data not only interpolated when we have missing points within that time series, because we need a continuous time series as well if we're going to do effective data-driven time series analysis. So one of the most common methods of dealing with both trend and seasonality is differencing. And so in this technique, we take the difference essentially of the observation at a particular instant. And then what we want to do, this mostly works well in improving the stationarity. So there's techniques, I won't go into too many details right now, but there's one called the Dickey-Fuller. So if you're statisticians and you're familiar with that, it's a very good test to quickly check and confirm that the production time series is stationary or non-stationary. And if you can run it through that sequence, and this is available in certainly Python. I've done this in Python. That test will give you a very quick understanding of whether it's stationary or non-stationary, and if it is non-stationary, what is it we need to do to apply and decompose that. And we can interpret this result using p-values from the test. So I won't go into too many details on that, but keep in mind there are some difference in techniques, which is a kind of a rolling mean, rolling standard deviations as we go through a time window. So you gate these times, and then these are overlapping, and then you use this this Dickey-Fuller test to quickly see if we have a stationary or non-stationary. Now, ARIMA is an acronym essentially that stands for Autoregressive Integrated Moving Average. And I'm bringing this one up only in particular because it's a technique that's been very popular in forecasting well performance. I think now we're progressing far more quickly now into deep learning, but that requires a lot more historical data, or at least a lot of different wells that maybe you could aggregate or cluster the wells that have very similar performance, because deep learning, long short-term memory, these are far more accurate, I believe, but it requires a lot more data. But from the limited data set that you may have, an ARIMA process is really good. It's a generalization of the simpler autoregressive moving average. So the AR part of it is the autoregression. So this is a model that uses the dependent relationship between an observation and some number of lagged observations. And then the I is an integrated. So this is the use of differencing, and I mentioned the differencing in the previous slides, of raw observation. So subtracting an observation from an observation of the previous time. So that's what I mean by the differencing, in order to make the time series stationary. And then the MA is like the moving average. So a model that uses the dependency between an observation and a residual error from a moving average model applied to lagged observations. And so these can be represented as 3 different parameters that go into ARIMA, known as PDQs. And these are the relationships and the functional relationships, but we don't want to get too much into the depth of that. But ARIMA is pretty good, and it generates outputs like correlation functions and autocorrelation partial autocorrelation functions, and these are important elements of time series analysis and forecasting, and it allows you to make some interpretations on how accurate this information is. I won't spend too much time on this. These are some of more the statistical ways of looking at how accurate a forecast is from using something like an ARIMA. MSE is just one of the many statistical quantity techniques to measure the accuracy of a time series. I'll let you research that one in light of the time parameters that we have. Now, the hyperparameters I mentioned before, these are more appropriate for your deep learning, because deep learning is what I find I'm doing more and more now, because you can actually accumulate quite a lot of time series data. You don't necessarily need 6 or 7 years of time series data for one well. You may only have 6 months to 10 months, maybe a year, but you have multiple wells. If you have 100 wells of 10 months of data, you can use a deep neural network. And the optimizer, when you implement a deep learning model for time series forecasting, some of these optimizers, there's probably a litany of these, 4 or 5, but I've listed some of the more successful ones here, and I'll let you do the research on some of these. But the Nesterov accelerated gradient is basically to try to understand how the weights within the neural network are updated. So we're looking at gradients between the errors that we get at the end of the first pass, and then we can use that gradient to reduce the noise within the as we go back through the process of going through the internal layers of neurons. We can actually change the gradients and so it changes the weights, and so these are pretty important areas, and I've tested pretty much a lot of these different techniques, and I think in summary though, the Nesterov accelerated adoptive moment estimation is probably the best one that I've seen for stationary production data in oil and gas. And this is something that came out of a Jupyter notebook that I threw in there using remember the autoencoder, the encoder decoder, and the NADM optimizer. Then you can have a loss function, the number of epochs, this number of iterations it goes through, and you could see on these set of wells that the oil rate, the historical oil rate, is in the blue, and it's pretty much the fit of the prediction was 84% accurate. So I will share this particular GitHub set of Jupyter notebooks, so that, and the data set is also there, so you can go through and look to emulate that yourself. So on the final slide, I just wanted to underline the 6 principles essentially of production forecasting, because essentially stochastic models essentially possess a lot of randomness, and the same set of parameter values and initial conditions can lead to an ensemble of different outputs. So there's a lot of randomness or uncertainty involved, but I think if you go through that iteration that I mentioned in the SEMA process and in the time series, in the decomposition, and going from a non-stationary to a stationary data set using techniques like the Dickey-Fuller, then I think you can get a forecasting based off of the production data that gives you a pretty good probabilistic forecast. Because remember, if you're using decline curve analysis and type curves, you're pretty much getting a single deterministic output, and now it makes a lot of assumptions about the reservoir. on the deep learning, the long short-term memory, and on the ARIMA, for example, in the machine learning world, we're looking at something that gives you a probabilistic range of forecasts, because no forecast is going to be absolutely 100%. And so short-term, long-term forecasts on production data, I think it's important to have a probabilistic range so you can have an upper and lower boundary. And in the case of Aramco, what they asked us to do was to every day make this forecast on 10,000 different wells. So you can pretty much do that very quickly. And you've defined your upper and lower boundary of acceptability of how much is going to be produced, how little is going to be produced. And then you can have some kind of output reports or a dashboard that of KPIs. And if you come in the morning, it will highlight in red all those wells that are either overproducing or underproducing. And they will be alerted to the engineer to say, okay, I need to go and see why this is this situation. Whereas if all the wells are falling within that probabilistic range of upper and lower boundary of acceptability, then you tend to leave those wells. And if there's wells that perhaps you are looking to abandon, and you may see consistent consistent real-time production that falls below the lower boundary of acceptability. So there's a lot of ways you can actually define your KPIs and percolate those into a dashboard, so that all you need to do is come in and as an engineer and say, okay, I need to go to these wells. These are problematic wells. These are good wells. These are bad wells, based off of these machine learning and deep learning techniques. So I draw a close there, Ria. So if there's any questions, I'm quite happy to stay around for another 30 minutes or so.
Sure. So Keith, I suggest, shall we take a break of 5 minutes and then we can come back with our questions? Everybody
Absolutely.
can take a water break and then we can start off.
Absolutely, yeah.
Okay,
No
thank
problem.
you. So it's we will join back at 5 minutes from now, so which will be IST 9:46. Thank
Okay,
you.
that sounds good.
Hi, everyone. I hope you all are back from your break. We will now start with the Q&A session. So whomsoever has a question, they can raise hand. There is an option in Zoom wherein you can raise hand and I will take your name, then you can unmute yourself and you can ask a question. All right. So whomsoever has a question can start raising their hands. Okay. So I see the first question I'll take from is Tawfiq. Okay, Tawfiq, you can unmute yourself. Keith, I hope you're here.
Yes, I'm here.
Okay,
Hello.
Tawfiq, you may start.
Hello, Kate. This is Taufik from ONGC.
Oh, hi. How are you doing?
Fine. You have a nice presentation and very encouraging presentation.
Thank you.
Actually, in our company, there are lots of data and we have to do data analytics for future exploration. You have a nice presentation and everything is clear. I just want to know if I want to start this data analytics part in Python Jupyter Notebook. Should I start from scratch by writing every code, so there are some open source materials available that I can use for doing this data analytics?
Yes. So if you're if you're familiar with Jupyter Notebooks, then I will send everything through Ria, but she can pass this on. I will send a Word document with all the links, all the URLs of all the different GitHub locations that I've used over the years, and I have some myself, and there's at least which area are you most interested in? Are you interested in upstream?
Yes, actually I'm a geophysicist and I want to do reservoir.
Okay, cool. Yeah, I could send you at least 6 really good locations which have data as well. So if you've installed Anaconda or Jupyter Notebooks, then you can definitely download those Jupyter Notebooks and run those. And they are very good examples because they are well noted. So they have a lot of notes in there explaining the different stages, etc. And then it's very easy for you with your own data to change or just change some of the programs or code and build your own GitHub resources as well.
Okay, thank you. And if in future I face some problem, can I contact you? Is it
Tawfiq, you can come through us and we will let you know how to move ahead. Don't worry.
I have to you, no?
Yes, you need to contact OGIS, okay?
Thank you for this.
No problem. Yeah, next question will be from Mahindra Pratap sir. Sir, you can unmute yourself and ask your question, please.
Hi Keith, I am Mahendra.
Hi.
I have worked with ONGC and also in the Middle East, and I am back to India now. So I was just interested, I was looking a fractured basement reservoir, and what I see that there are 2 or 3 wells which have signature of ideally fractured reservoir. But some of the wells are quite away from the fault, but they are the best producers. I mean, when I talk about the fault, I'm talking about seismic fault. I don't have idea about any subseismic faults in that field. Yeah. So how do you like use any kind of understanding from machine learning or something like that in this kind of situation?
Okay, so if I understand correctly, you're looking at unconventional, where you fractured
Yeah,
the rocks?
it's a basement reservoir, Deccan Trap. If you know Deccan Trap in India,
Okay.
yeah. So it's like maybe basalt rock,
Okay.
typically basalt. Yeah.
The basalt rock.
Mm,
Huh,
mm.
interesting. So, so your question really is to try to understand the high level forwarding system as opposed to maybe a generated fracture network that was created by the hydraulic strategy. Is that what you're asking me?
Yes, 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 yes.
Yeah. So it's
I'm
interesting.
talking about the natural fractures. I'm not doing any
Yeah,
hollow
the
fracturing
natural.
job.
Yeah, the
Yeah.
natural fractures that are in the
Yeah.
network. Yeah.
Yeah.
So yeah, we did some work with Aramco in more conventional reservoirs in their carbonates, where
Mm.
their natural fracture network, they, as you can probably appreciate, they couldn't exactly tell where, but they had a good understanding because it was important for them to place their injector wells in the right place so that the fluids, the water drive project, didn't go into these thief zones and go up fractures that they didn't anticipate, but went towards the production of the hydrocarbons. So what they try to do is they try to intimate, if you wish, or try to indirectly measure the fracture network by looking at the responses of water cuts in different wells and trying, because the fluids, if they didn't go down the natural fractures they had on their geologic model, then either they assumed that those fractures were incorrect or the network was more complicated if the water cut was much higher. So if you have, I mean, do you have hard data that measures that, or, you know, from the seismic is the best place? I mean, just go back, let me step back a bit. The best, I was a geophysicist at Shell for many years, and the best way we saw that was to generate seismic attributes. And there are like cohesion and other types of attributes that are reflective of the fracture network. And if you could go to the seismic data and generate some of these attributes, and I know Schlumberger and Halliburton have some pretty good software that enables you to generate some of these coherence, and you can see discontinuities based off of the seismic attributes. And then you could take those seismic attributes that are representative of the fracture network and run them in a neural network in order to try to map those to your reservoir in geologic model. So you've identified, like, I mean, at every well location, you have pretty good idea of the rock properties and other characteristics of rocks, but in between, you may not understand the fracture network. So if you have the seismic attributes at between the wells that you can generate from the seismic data, then you may be able to map that across between the wells using the seismic attributes.
So I mean, you are you mean that even the subseismic level features like fractures or a small throw faults can be identified using this kind of analysis?
Yes, yes.
Okay, thank you.
Thank you, sir. Now, next in line is Manjeet.
Hi Keith, this is
Hi,
Manjeet.
Manjeet. How are you?
I'm good. How are you doing?
Good, thank you very much. Yeah.
Yeah. So as I told you yesterday, my question would be related to computer vision. Okay. If you say, if I'm trying to automate some vendor drawing inspection, my problem statement would be from the engineering design work for the refineries.
Right.
Okay. So I would like to know, how can I employ this kind of technology, this computer vision technology, for automated this drawing inspection?
Right.
And can you suggest me some good algorithms with which help of which I can achieve these my goals?
Right.
I hope you can read my question in that window, chat window.
Um,
Mm,
did you just put it there? Or?
yeah, I put it some time ago. Uh, uh, okay, wait. I will try to put it again.
Okay.
Ria, can you
Actually,
paste that?
no. Actually, you'll not be able to send the chat to Keith. If you want, I can read it out for
Oh,
Keith. Okay. Let me just try. Manjeet, can you resend that query to me?
yeah.
Because
No. Otherwise, I will read it out. Not an issue. I will
yeah,
read.
please do. Thank you.
Can we employ CNN for object detection, and also at the same time, can I employ OCR techniques to read the fetch the object information and the text information at the same time from the vendor drawings?
Yes, yes. I have seen some technology certainly used in refineries where they try to make a digital twin of the refinery, and also in a well where they try to make a digital twin of a well. So, OCR techniques where you're looking at templates, maybe blueprints of your refinery, and
I'm it's not okay. You are talking about some you're referring to plot plans or something like that?
yeah, yeah.
No, okay, plot plans is a big thing, but I'm going to start with this assignments. I'm going to target few small things like vendor drawings of the equipments.
I see. Okay. Yes, you should be able to scan those into, I mean, unstructured data is one of the most prominent data sets in oil and gas. Actually, it's far more common than nominal data or numerical data. And so with text analytics, and if you have PDFs or any kind of written daily documents, you can actually transfer that into a numerical data set. And if it's pictures, such as blueprints or anything like that, it's important to be able to capture the knowledge of that, and you can do that through text analytics as well, and then aggregate that with numerical data. Some companies I know are very good at that process. I can send through OGES a couple of companies that do a good job for that in refineries, where they will take any of your pictures or your maps or any of the blueprints, because that's the first thing you need if you want to build a kind of a digitalized twin of the operations within your refinery. Or
Okay.
is it?
Yeah, thanks, Keith. And one more thing, like suppose if I'm employing these algorithms of this CNN for object detections in the drawing,
Yeah.
do you know? Can you suggest me some good line tracing algorithms? Like if suppose if I want to trace a line which is coming from one part, like from one part of the drawing, and it is connecting to some other part of the drawing, then can I just trace the line from where it's coming and where it's going? So line tracing algorithm, I have heard something of that, but is it real? Is it ready-made available on GitHub or something like that?
That's interesting. So you're talking about like a picture with lines drawn on it, and
Correct.
now what are you trying to optimize there? Is the line going in the right way, or right?
No, I'm just trying to figure it out that which line is connecting from which equipment to what equipment, something like that.
Oh, okay. Yeah, I mean, essentially, you can you could train. There are some convolutional neural networks that don't just, you know, they essentially it's a classification technique. So if you had lines connecting, you know, have you ever heard of Feynman diagrams, you know, where you're trying to connect things together that have some kind of underlying meaning or interpretation, you can actually build that into the parameters of a convolutional neural net and train it. There will be some input from you as an engineer to train it to in order that it classifies it correctly, but you could do that. Yeah.
Correct. Okay, thanks.
Okay.
Nikit. That answers my questions. Thanks a lot.
Okay.
I will get in touch with Ojes for further any clarifications.
Yes.
Sure. No problem at all.
Thanks.
Okay. Thank you. Now, next question is from Joseph Kallio.
Hi, Joseph.
Okay. Good evening.
Good evening, Joseph.
Good evening, Raya. So, while going through your presentation, you spoke a lot about the CNN, right? And I see you focus more on trying to get footprints, right? Images, and you use that for your data analytics. So my question is this: is this really important, or how critical? How can you deploy this in terms of surveillance, right? What I mean by surveillance, I'm saying, for instance, where you have interferences into your operations, how do you use this to monitor those interferences? Here in Nigeria, this is actually a problem, you know, within our operations, where you have a lot of security interference to your pipelines and so on and so forth. So we deploy these, you know, in terms of trying to manage these problems, situations, so that we are able to proactively react towards those incidences.
Yes, that is a very interesting question, because I did work for Shell in Port Harcourt for a little bit, and
oh, that's interesting.
Yeah, and so a lot of our pipelines were being broken into, and people were stealing the gas and stuff.
Yeah.
So what at that time, though, this was in the 80s, so we didn't have the same technology. Then I think we were just flying helicopters up and down. But what I understand from some old colleagues of mine who work at Shell, they said they have some technology. I'm not sure if they're using drones, but they did mention that the intention was to fly drones over the pipeline, for example, taking video and audio to basically see when these events were happening. So I understand that what the data they would collect a lot of historical data, and then they would use these techniques to predict potential, because they would see, for example, through patterns of analyzing the video, where the most common places were for some of these, you know, where people were breaking into it and where there was security problems. And they could even monitor in real time the location of agents, they called them agents, that were potentially going to cause these security breaches. And it's based off of a technique that actually New York Police Department use right now in Manhattan to predict where a car is going to be stolen. And it's because, believe it or not, a lot of these people who commit these crimes or security issues act in patterns without realizing it. And so it's a kind of a pattern recognition technique based off of the video from drones, I believe they were collecting. So there are ways. I'm not totally familiar or an expert in that area, but I can talk to my old colleagues at Shell to see what they're doing with their pipelines. If that helps, and I can send that through Ria to send to you.
Okay, that's fine. Thank you.
Thank you.
Great, thank you. Next question is from Rishikesh. After this, we will only take 2 to 3 more questions, please. All right. And don't worry, if you have questions, you can email them to us on support@ojs.info. And like we promised, we will connect with Keith, get those answers, and we will email them to you. So Rishikesh, you can ask your question.
Thank you very much, Ria. So first of all, okay, I'd like to thank Keith, okay, for these engaging sessions. I think you have been, you presented quite brilliantly over the 2 days, starting from yesterday.
Thank you.
So, let me ask you another question. So, I have been working on this ARIMA technique, okay, for a while, I guess, last 6 months, and I've been seeing, and I can see that ARIMA uses, it's a univariant model. So if I want to incorporate multivariant model, so what are the other algorithms that I can try, for a production focus?
Right.
Let's say.
Right. What is the time series data that you're trying to forecast?
Like oil rate, I'm trying to forecast.
Oh, okay, sure. Yes, so I will send to Ria 2 papers that some colleagues of mine at Petronas in Malaysia, and also in Shell, used to do prediction of oil and gas and water rates based off of not just production data, but also test data. So when they shut the wells in, they were using testing data as a technique to try to understand the technical potential from some of the NOCs. So these 2 papers were written for the SBE, and it defines about 4 or 5 different what we call ETS or time series. ARIMA has 2 or 3 different types, but it goes into details on UCM and about 3 or 4 others, and I can send those to you. There are different ways, but it's dependent on the quality of your data as well. So there are important factors to remember there, and then you can compare the models. Do you use open source or anything like that?
I'm using Python in
okay.
The software that's all Anaconda I'm using.
I can send you a couple of Jupyter notebooks that also do this, and then you can see the techniques that are being used. But Petronas have used 3 or 4 different techniques that are very, very popular, and I will send those as Jupyter notebooks to you if you wish, and a paper.
Okay, that would be great. Thank you.
Thank you.
Thank you. Next question is from Mr. P.K. Penoli. You may ask, please.
Yeah, thank you very much. Thank you, Keith. So I'm from University of Petroleum. So my question has two parts, small ones. First is, what is the predictive performance of the unsupervised phases, seismic phases classification in case you don't have many wells? That's
Right.
number 1. And the second part is on the application of data analytics with reference to making a digital rock volumes from the high resolution images of the thin sections.
Well, the first question, if you have limited data, then obviously you want to stay away from any kind of deep learning techniques, but the unsupervised support vector machine is very accurate with very limited data to do fascist classification, and we've seen it on maybe just only using 3 different well logs, and probably with about 2 dozen wells, and it did a pretty good job. But the biggest problem is the generalization. So if you took that algorithm to a different part of another country, for example, or a different field, then you may need to train the model. You don't necessarily have to change the model or the sequence of events or sequence of steps to build the model. You just have to retrain it. But limited data, sometimes you can generate pseudo data from the limited data, and I will send you a really good paper on. I mentioned it in I think it was on day one about imbalanced classes. So if you have limited data, you can actually populate with pseudo data that helps to train the model. But support vector machine is fine. It's the deep learning algorithms that have a problem with too much data, or too little data, sorry. Now the second question, could you please repeat the second question? I think
the question was on digital rock. The predictive making predictive or a virtual rock volumes from the thin SAM, from the high resolution thin sections.
So you're looking at thin sections under a microscope of
yes,
rocks.
Yes, the point counting, yes.
And you're recording certain petrophysical properties from those thin sections?
Yeah, that's the idea.
Yeah. And so the question is,
what kind of algorithms? Yes.
What kind of models?
Yeah.
You can use on rock properties to. Are you trying to?
Yeah.
Are you trying to predict the reservoir characteristics within that particular area where you?
Yeah, within that rock volume, which is being built from the thin sections, 3D volumes. I intend to run my flow characteristic or reservoir characteristics within that volume. So whether the machine learning and the AI, if you want to advise anything on this.
So it's like a classification.
Correct, absolutely.
Yeah. Yeah, certainly. Like I mentioned before, there's several. A classification technique is invariably supervised. So if you had several features or properties or parameters, and then the values of those that you've basically read or interpreted from your thin sections, if you tabulated that information, you could probably even cluster to see what the common value ranges are for each of the different features that are representative of a particular rock or mineral. Because I've seen this used in the, I mentioned cut-ins from drilling, where they've used the different the cut-ins to classify what are they representative, what rocks are they representative during the drilling. So I'm not fully understanding your question, but if you there are techniques for classification for sure if you're trying to classify the different rocks based off of the readings you see under a microscope. But I'm not sure how that what your goal is what I'm trying to understand.
Right, thank you, Keith.
Thank you.
Okay, next question is from Gaurav. So, and this is the last question that we are taking today. So thank you, everyone. Gaurav, you may ask. And after this question, we'll have a small presentation, a 5-minute quick presentation about OGIS. And then after that, I'll also answer your queries as to what all you can expect to get in your email or how we plan to share the information with you. Thank you.
Good evening, everyone.
Good
First
evening.
of all, Mr. Keith, excellent presentation. It
Thank you
has been
very
a
much.
marathon session for you. And let me tell you, it has always been pleasure listening to you and your insights on application of machine learning and artificial intelligence in upstream.
Appreciate it. Thank you.
Yeah, and for other participants, some of you may be aware, and if for those who are not aware, Keith has authored few books on this topic. They are definitely must-read book if you are interested in application of these technology. And I would also take this opportunity to thank Ria, Saurabh, and entire team of OJAS to organize this training. It has been really fruitful for everyone for every one of us. Thank you once again, Ria.
Thank you so much.
Coming to my query, it is related to reservoir simulation. Mr. Keith, for something as complex as reservoir simulation for production forecasting, these days we come across companies who pitch us on application of hybrid models, and which has a blend of physics and machine learning. I would like to know what are the possible ways of this hybridization. Secondly, which part can be, so to speak, can be taken care of by typical physics, and which part is preferred by machine learning based algorithms? This is my first question. And second, I would like you to quickly touch upon what is the status of top-down reservoir modeling in terms of how mature it has become to be adopted by upstream industry. Thank you.
Right. Very good questions. Yes. So I'm not sure, Gaurav, if you're familiar with Shahab Mohageg. He's someone I mentioned before.
Yes.
Yes. So he and I talk quite often, and I have the utmost respect for him. He's one of the leaders in this area, and he proposes this top-down technique and top-down modeling, because before there used to be surrogate reservoir models, and they don't work so well. But when it comes to simulation, numerical simulation and numerical simulators in oil and gas, there are a few people who really do not trust the data-driven approach. They just think it doesn't work. But if you listen to Shahab or read his SPE papers, and I've advocated that myself a few times, we've done this, where the first principles we use as constraint in top-down modeling. So you could actually run a reservoir simulator from Schlumberger or anyone, and take the outputs of that simulator and just maybe for one part of the field, and that can feed in as data points and enrich a top-down model where reservoir characteristics and first principles are not considered to be the driving force. It's the data itself. Like if you have all the reservoir properties from well logs or cores or whatever, and then you do a data-driven approach, and so the reservoir characterization process can be constrained by first principles, but at the end of the day, it's the data that's telling you what's going on, especially the production data that's gone through the reservoir and has a lot of fingerprints on what's going on. So I think the top-down model is being more readily accepted, and the numerical simulation, I know Shahab, he advocates taking maybe some of the traditional simulation output and feeding that and enriching the data-driven approach. Because so I think having talked to Shahab and seen it myself, I think there's a lot of value, because you can actually get a pretty good simulation by instead of just changing one parameter at a time, you can actually see the values of change in porosity very quickly in a top-down model using a data-driven approach. But there are constraints, obviously, of first principles, but I think the most important thing is to not just aggregate all your different types of spatial or time series data, but also maybe run a numerical simulator and take some of the output points and enrich your data set to do that from a top down. It's these proxy models or whatever, they're not as really as comprehensive as the top down modeling techniques, and I really do advocate that myself. So.
Okay, thank you very much, Mr. Keith.
I will send Ria some of the papers that I talked to Shahab last week, actually, because we both work on a committee for the SBE, and I will send you the latest off the press from Shahab through Ria.
Really appreciate. Thank you.
Okay.
Thank you. Thanks a lot, Keith. So, Keith, I know we have already gone past time, but I'll take another 5 minutes, and I would request all the audience as well to, first of all, thank you for your patience, and just need 5 to 7 minutes of your time more. I'll quickly share a slide with you.
Sure.
Yeah, so I'm not as good a presenter or orator like Keith, but I will try my best to make sure that at least you understand what I'm trying to say. Okay. Now, OGIS, as you are aware, and as I mentioned earlier also, we are a oil and gas company, a consulting firm which makes digital solutions for the oil and gas industry. So far, OGIS has made 8 such solutions, which I would like to touch upon briefly. So the first one, as you see, I hope you all are able to view my screen now. Yeah. So the first one, the good thing is, luckily, all the names of the solutions are self-explanatory. Okay. Just give me one moment. I have received some chats. Okay. All right. So you can see my screen. Thank you. Now, the first one is the knowledge management system. We also call it OGIS Knowledge Acquisition System. And OGIS has signed an MOU with a government entity in Oman, and there we signed this with 46 companies, out of which 5 companies in Oman are using the system on trial basis. So what the knowledge management system does is it helps oil companies in having a software within their organization wherein global experts are online to solve their queries. So there are global experts either from India, Europe, America, who are available on certain times every day, and you can choose which consultant you want to discuss your query with. You can either do it through the web forum, on phone, or even for a small consulting assignment, you can consult with them remotely. Now, due to COVID, on-site consulting is a bit, not possible, but that is also an option given there. And this particular solution has been running successfully with a few Indian companies also, wherein they use us for short studies and customized trainings as well. So here we do get a lot of, help in order to generate business, as well as help clients do short-term assignments with the help of these global experts. Now, moving on to the second solution. Again, as I said, the names are pretty much self-explanatory. So this is Well Services and Planning and Look Ahead Management System. We have already procured one client, and we have about a 2-year contract with them. And this particular software obviously helps companies to plan their look ahead and organize their well service units like coil tubing, wireline, pumping, slickline units, etc. And they can organize their intervention opportunities. Then the third one we have is Completion String Management System. Again, we have a contract running, an active contract for the system. And this system also helps oil companies to store their old completion strings, their completion tallies in a structured format. And all the old strings that are there in Excel can be quickly imported in the software, and new completion strings can be made from the software itself. And one of the oil majors is using it. The fourth one, just give me one moment. I have another message. Okay. Okay. So regarding more details about these, solutions, I will be in touch with you on individual basis, one-on-one basis. We have sent out a form wherein you can tick which particular solution you are interested in, and I will come back to you. I'll call you myself, or the concerned team will get in touch with you. Now, the fourth solution is production monitoring and reporting system. Again, we have secured one client, and this is on renewal basis yearly. So this software, again, it helps oil companies in production monitoring by you can daily input your data here from different departments like the production unit, tanker unit, HSE, etc., and get a consolidated report for different stakeholders. And this report can be downloaded in Excel or PDF. Next one is RFQ management system. Again, we have one client for this particular system as well. And this is a very robust and good solution wherein it allows the companies to create their RFQs on its site and then invite multiple manufacturers and vendors to provide quotes. It's very usable in terms of the user experience is very good, and we have received very good feedback. The sixth one is pertaining to my domain. I head this division at OGIS, that is the recruitment. And here also the recruitment is done via our OHIRE recruitment management system, wherein we install the system in the companies, with the help of the HR and their IT team, we install it there. The good thing about the system is, apart from, like the normal ATS, obviously you can post jobs, you can invite candidates, you can schedule interviews, but along with the ATS, you also get a database of your particular industry to choose from. So if you have other databases, it helps in cost saving as well, because then you can say you don't have to pay for those. Okay. Then seventh one is, this is pretty impressive and interesting to someone like me who is not from pure oil and gas background. This is the stop card reading system. And this software helps in reading handwritten stop cards. And then it stores the information in a very structured manner. And this is done using artificial intelligence. And it can read multiple languages, just not English. So if someone is interested in knowing about this system, they can reach out to us. Then the last and the recent one that we, along with the stop card reading system that we created, was stop card entry system. So what this system does is, this software helps in entering the stop card details on a desktop and mobile based application. So what happens is, if there is any a situation that needs quick attention, then the management and other stakeholders can quickly look into it sitting in their offices and can provide the solution or take a measure for it. So thank you. These were the 8 systems I wanted to talk to you about. We, as I said, we have sent out the feedback forms. Please do take 2 minutes time to fill those up. It helps us better our services. And that's all from my side. Now, coming back to the digital presentation, Keith, thank you so much. I think you did a commendable job, for someone like me who is not a pure oil and gas person. I will not say I could understand the whole training, but yes, I could understand quite a few parts of it. And we got many appreciation from all the participants. Once again, thank you so much for your time, and thanks a lot.
Thank you, Ria. Thank you for organizing everything, and thanks to OGIS, and thank you very much for everyone attending. I really appreciate your time.
Thank you. And dear participants, thank you everyone once again for your patience. And I think you were amazing audience. Now coming to, as promised, we will share the slides from the presentation and the notes that Keith has, technical papers, Word document of references, and link to GitHub Python programs. But all these things will be shared with the paid members of from the participants. Also, regarding the recording, a lot of people ask me this question, and I've received emails as well. So once the recordings are ready, we will put the recordings on the YouTube channel of OGIS, and we will share the link. Okay, again, this will be for paid participants, so they can listen to the recording there. And regarding the course material, etc., this will be made available to you by end of first week of September. So that is either that would be Friday next week, or earliest by Monday next to next week. Okay, and you can always get in touch with me if there are any queries, or if you wish to get in touch with Keith. Also, this was a certificate course, so you would also get a course completion and or a participation certificate signed by Keith. Okay, so this will be given out to all the participants. And for any questions, anything that has remained unanswered today, you can again reach out to us. My email ID is support@ogis.info. You can reach there, or sales@ogis.info. And my personal or official email ID is ria@ogis.info. Thank you, everyone. So I would like to now, this is the end of the meeting. Once again, thank you, Keith. Thanks, Elena. And thank you, participants. Bye-bye.
Thank you. Thank you. Bye.